Okay, guys, good morning. If you remember, we were discussing material jetting and binder jetting. This was some of the fundamental additive manufacturing techniques. We briefly said that in material jetting, the head is actually responsible for jetting the main material. It may be in different forms, but this is a fundamental thing. And on the other side, for the binder jetting, it's kind of similar to powder bed fusion systems. We spread the powder on the bed, and then instead of using lasers, we actually jet binders, and these binders will be responsible for joining the powders on the bed. And this can be used for various types of metals, for ceramics, even sand, for metals, polymers. There are different companies and using the same approach for various materials. Now in this part, actually part of the chapter, we'll be focusing on some research achievements in especially polymers and polymer materials and during this deposition. And these are mainly for material jetting, not for binder jetting, but we will discuss some issues with binder jetting in a moment. First of all, in this material jetting, you can use different types of jetting techniques, but the fundamental idea is the same. At high speeds, you need to deposit this material on the substrates, on the initial material, or on top of the already deposited material. And we don't have much literature in terms of material jetting on different journals, but there are some. These people are focusing on different aspects of, let's say, deposition. And they try to compare the deposition frequency and the columns, the quality of the columns they are generating. And also they compared the deposition frequency for the lines. Now let me show you. This is for columns and this is for the lines. As you see here, we have frequencies starting from 0 to 500. And in this two example, we are assuming that the speed of movement is the same. So they are moving at the same speeds for all the cases. Okay. The only thing is that while they are moving at the speed, they deposit 500 times in a second. But here, obviously, it shouldn't be exactly 0, but at least they are depositing just once. And here, for instance, in a second, they are depositing hundreds, let's say, drops on this column. And if you look at the quality of these, I think this might be the best one. It's a bit thicker, but at least it's fine. This one is a bit, actually has such kind of blend. So that's why I prefer, if you look at this columns, I would prefer 20 depositions or 20 deposition frequency. And on the other hand, we have the lines. So this is 2D. They are moving from, let's say, left to right. Again, for all these cases, the speed is the same. This time let's use V2 as V1. And on here, as you can see, the frequencies of deposition once again. And if you deposit, let's say, less number of drops while moving from left to right at a defined speed, you see that we have discontinuity. We have drops after each other, but we don't have a continuous line. And if you continue increasing your deposition frequency, obviously these dots, these drops will be joining each other. And at that point, at actually around 700 Hertz, you see that we have a perfect line. But if you increase this deposition frequency furthermore, you will see that we will have extra material and it will not be easy to control the thickness of this deposition. So if you are moving on the plane and if you have predefined speed value, then that is the deposition frequency you should use, 690 Hertz. Any questions, guys, on this research paper?
Hocam ben material jetting hakkında bir şey sorabilir miyim?
Yep.
Material jetting'de Depozit edilen materyaller nasıl birleşiyor? Ben o kısmı tam anlayamadım.
They are usually in semi-solid state. These ones are kind of waxy material. So once you put them on top of each other, they will be joined. Not completely liquid, but in a kind of semi-liquid state and waxy kind of material. So it's not difficult for them to join together. Obviously, they're not solids. We cannot have solids joined together just by high-speed jetting. So did you watch the videos actually in the previous slides? In the last lecture, I didn't show them to you, but you were responsible for watching. But I think none of you have watched.
I watched, but I couldn't understand the videos.
Okay, let's please, I will show you one of it. So here we have the material jetting system. Let me try to open this one. I'm looking for one actually showing the deposition. Yes, this one is fine. And I will also show you another one, this one. Okay, let me share the screen with you. This is the first video, a very primitive one, since right these days we don't have any commercial systems applying especially material jetting. It's a very primitive one. This is model maker 3D printers. So they have a kind of an head here, and it's jetting material on the substrate. This red one is the jetted material, and they are all in kind of waxy state. This is another one. Let me start from here. It's called thermojet. Material deposition by jetting. And again, they are jetting kind of polymers, some waxy polymers, using again support structures. Always they need to use wax-like material. For other materials, it's quite difficult to have material jetting. Any questions, guys, on these material jetting or on this research, how they obtain the optimum deposition frequency for the columns and for the, let's say, layers? Okay, let's have another work. In this one, they actually play with the speed. In the previous one, they actually have taken the speed as a constant, but this time they are modifying the speed and try to obtain again a proper velocity for the droplets. And again, they are using wax material, and you will see that in the, let me show you the next image. Here you can see we have two different, let's say, set of experiments. This is the first set of experiments. In this one, they have low droplet speeds, which means that they are actually jetting the material at very low speeds. And on the other hand, they have two options for low droplet speeds. They may have a low speed on the plane or a high speed on the plane. And obviously, once you have high speed like this one, you will have discontinuous lines. But if your droplet speed is slow, then that means you should also move on the table at lower speed. If you have it, then you can obtain such a nice line, but for other case, you will always obtain such discrete portions, discrete lines. On the other hand, if you increase the speed of your drops, which means that jetting speed is increased, if that's the case, and if you use it for also with high speeds, let's say, speeds on the table, you'll have splash around the table. You see, this is the case D. We have some splashes around, so it's quite difficult to control the resolution. But if you decrease the speed while jetting materials at very high speeds, you'll obtain some bulges, such like extra material around your line. So in summary, we can say that you should find is optimum speed for the droplets and also optimum speed for the movement of your head. Any questions, guys, on this research, how they obtain how they perform actually kind of set of experiments? We have two variables, speed of drops or the frequency of drops, and the other one is speed of the head on the table. We have another study. This is not complicated, but they are trying to obtain such complicated shapes having smaller features. And again, they are using a wax material. They try to control this pattern with the help of adjusting the size of the drops, adjusting the speed of the drops, the jetting speed, and also the speed of movement on the table. And the parameter they need to adjust is the spacing between the hatches. If you remember hatch spacing in stereolithography or in SLS systems, we have such spacing, and this is also valid for kind of material jetting. For instance, it may be going like this. This is called as hatch spacing. So depending on the amount of material you are jetting, you need to adjust this hatch space properly. Another issue I forgot to mention is that about the temperature. You should heat this wax to an amount which is higher than the melting point temperature, so that it will be easier for they actually have to generate drops out of this wax material. And on the ceramic side, again, people have some similar experiments, similar studies. They focused on sweep speeds, the actually scanning speed kind of, drop-to-drop spacing, the substrate material. The substrate material, actually initial material they need to work on. So you need to have a kind of substrate, and on top of this substrate, they will start jetting material. So the type of substrate actually determines the quality of your printing process. Again, line spacing is important. The form between the layers are important, how they are bonding each other. This is important. And we have some other studies in literature, and they use different types of powders, zirconia, and other additives. And they come up with a solution that they need to have a quite larger nozzle, and they need to keep the substrate quite away from the substrate. So there should be a kind of a gap, and this gap is about 6.5. But again, it depends obviously on the type of material you are using and the nozzle diameter. Here are some experiments, but not important. They should find proper parameters so that there will be a nice, let's say, fusion between these generated drops. I think this might be the proper case. And another issue about the ceramics is that if you cannot just jet material itself, then what you can do, you can have a kind of a wax carrier. So assume that this is the original aluminum particle, which is ceramics, as you know, and then around it, you may have a kind of an wax carrier. Assume that this wax carrier is blue, and you will have around this material some blue wax. That will actually carry your main material. This red one is the ceramics. Actually, we want to have our product fabricated with ceramics, but in order to make this printing process simpler, we need to use a wax. And with the help of this wax, other, let's say, particles will be joined together easily, since that might be in kind of a semi-solid state. But if you simply jet aluminum particles, they will not be joined together. So that's why they have a kind of a simple solution. So there are many research on this type of carriers. So the thing about it is that if you have too much amount of carriers, then you will have higher viscosity, actually lower viscosities if you have too much, but the high concentration of the powder aluminum particles will result in high viscosity. So you need to arrange the amount of carrier and the amount of particles, original particles you want to have. And another issue, once you follow such an approach, is that you need to obviously do some burnout and sintering process. In the burnout process, we completely remove this wax, since wax can easily be burned out. You can get rid of it. But for joining of the ceramic particles, we need to do further sintering. In this case, if you do it, obviously we're gonna have some porous, probably maybe up to 20%, 25% of the whole part will be porous, and you may need some extra infiltration or impregnation. And after the sintering, obviously, since you are joining these aluminum particles together, they will decrease the amount of porosity you have before sintering. But the problem is that the shrinkage, and since they are joining together, the overall size after the green part will be decreased, and you need to be aware of this shrinkage percentage and design your parts accordingly. Any questions about this issue?
Hocam ben aslında genel olarak bir şey soracağım. Bu jet edilen materyallerin %100'ü kullanılabiliyor mu? Yani %100 oranda mı o part oluşturuluyor? Yoksa bir kayıp oluyor mu?
No, you can, if your parameters are fine, if you are not jetting your material to somewhere else in the table inside the machine, you can use them completely. So we are assuming that all the parameters are fine and you are jetting this material into the right side, then obviously you will be using the whole material. Yes, depending on the complexity of the shape, your friend pointed out, we need to use support structures as we have seen in the video. Since we don't have built kind of beds for the material jetting, we need to have support structures. But for binder jetting, we don't need to have supports, again, especially for polymers, since the fabrication is done inside a bed. And on the material side, material jetting side, we need to use support structures. Yes, Bilal?
Hocam green part dediğiniz wax mi oluyor?
Yes, the wax, and inside this wax we have the aluminum particles. This is an example, and we have a kind of a video. I will now show you this one. And as you see, the amount of ceramic is not much. It's just 14%, but still it has some of the properties of ceramics. Let me put it first and then share it with you. It's a quite long video, so I will skip some of the parts. Yes, now they are trying to use ceramic powder and try to have some complicated parts. they can produce such cups.
My name is Stephen Hoskins.
But I will ask you the type of process they are using, whether it's a material jetting or a binder jetting.
You can print in metal. You can print.
You see, they can also have such lattice structures.
What are known as photopolymeric material, first large printing for artisan. That we could AHRC funded manner.
I will come to, yes, this part, I guess.
So that we can now actually print in a real ceramic material that has the same aesthetic and quality as other ceramics do, whereas previously for prototypes you're printing plastic or plaster materials, which don't have the same surface feel or quality or tactility. So that it allows people to be able to print an object with just that right look, feel and aesthetic that you wouldn't get anywhere else. The partnership with Denby has allowed us.
So they have a kind of a CAM software, prepare the slices. Yes, now this is how they are printing.
We have a bin, a box of powder, and if you imagine that box being quite empty with a plate at the top of the box, you have a thin layer of ceramic powder. If you're printing a cup or a plate, you print a small ring at the very bottom, one thin layer at the bottom of that cup or plate, and then it drops down one step, and we push more powder over the top. Then it will drop down another step and push more powder over the top. And you print one single layer at a time and slowly build your object up in thin layers, which is why you can print incredibly complex shapes, because they're just supported all the way around by powder as this shape keeps dropping down. Finally, when the whole thing's printed, it's left to dry in the bin of powder, and then after an hour or so, you lift the whole plate out and dust all the powder off the object, and in the middle of there, you have an object.
They are recycling the powder.
That object needs drying further, so we put it in an oven to make sure it's really quite solid, before we then put it into kiln and fire it. That's known as a biscuit firing, the first firing. And at this stage, that's where it becomes same as a normal ceramic process, because you would have a biscuit firing in ceramics. So we biscuit fire it to a temperature and then take it out of there. You can then glaze the object and refire it at a higher temperature for the glaze to go over the ceramic object. And then you can have a third firing if you decorate, where you would refire the decoration on top. But you will always have at least two firings. In terms of...
So these are actually the things required for ceramics fabrication, the firings and putting it in the oven. But up to that point, we can call that as a kind of a printing process. So what do you think this process is, a material jetting process or a binder jetting process?
Binding jetting process.
Yes, binder jetting, as you see, they have a kind of bed and they are simply jetting some special binding agent so that the ceramic powders will be joined together. And after the part is taken out of the printer, it's not finalized, it's called as kind of a green part, and you need to do some further sintering and burning operations. Let's have a look at the metals. We also have some material jetting for metals, but it's quite difficult, since if you want to jet or generate some metal drops, you need to have, then that means very high temperatures. So that's why we mostly don't use material jetting for metals, since you need to have highly powerful, very special machinery. Instead, we only use for some simpler metals, like having low melting point temperatures, for instance, solder, especially for integrated circuits, we can make use of such an approach. And there are also some studies like on copper, aluminum, but for difficult materials, for steel, obviously we cannot have it. And mercury, as you know, is already in the liquid state in room temperature, so you can kind of have some special operations and try to print it. So the most important issue is the melting point of these metals. If they're high, it will be almost impossible to have them in the material jetting processes. So for instance, you see there's an example, they jetted and kind of an alloy, and the melting point temperature of this alloy is just 47 degrees. If that's the case, if you have such combinations of metals like alloys, you can do material jetting with metals, but we prefer to do binder jetting with metals. So we have some obvious achievements in literature. It's a kind of a different process for 3D printing. We can use them obviously for prototyping, for electronics industry, but we may have some different approaches in the near future. But in summary, it's quite difficult to use metals for material jetting. Instead, we prefer to use binder jetting for the metals. On the other side, for polymers, it's quite okay, but the studies show that the easiest material to jet is actually the wax material. If it's in kind of wax state, yes, you can use it in the material jetting process. So what are the main challenges in these jetting processes? First of all, we need to have a kind of a liquid material. So if you cannot obtain it, then you cannot have successful results, nice prints in these jetting processes. Since if you do not have the liquid form properly, then that means you need to follow different approaches. For instance, what you are going to do, as in the case of alumina and wax material, you may have your original material, which is suspended in a carrier liquid. Or you may have dissolved materials, or have some melted polymers, or you may use some mixtures of monomers with photoinitiators. Once they are jetted, then you may do the curing on the fly with high UV values. This is also doable. And lastly, you may also have some special surfactants which are added to the materials so that their mechanical properties will be at least acceptable for jetting. And in the jetting, the biggest challenge is actually in the droplet formation. We need to have drops. If you assume that this is the head, and we will have kind of a nozzle here, and we need to generate such drops properly. And the thing is that they should be generated at very high speed. Maybe in a second, we need to generate thousands of drops. And for that purpose, we need to use special hardware, special materials, and that's actually make it quite challenging for jetting processes. So what we are going to do for jetting, we will start with a continuous supply of liquid material, and they will be turned into smaller droplets. And for that purpose, we need to have special material, we need to have special hardware, and some proper process parameters. Again, this is important. If you cannot adjust the speed, the frequency of drop generation, you will simply fail. So as I mentioned, in this jetting processes, you need to control the deposition of these drops, the speed of it, the path of these drops is quite important. Are you going to have just a direct path or an inclined path? They are all important, and they will be affecting the overall quality. Another impact strength of your materials, the speeds. These are the critical issues in jetting processes. And its interaction with the substrate is another important issue. And obviously, the trajectory of our droplets depend on the velocity and the size of drops generated. And lastly, the quality of your drops should be actually maintained as you are colliding with the previous drops or colliding with the substrate. So these are the critical parts, and as you see, there are many critical issues. So in summary, we can say that this is a bit difficult process to construct. So you may have the phase changes since there's a printing process, and at the end of the printing process, we want to have a solid product, right? We cannot maintain the shape of liquid or semi-liquid materials. We need to somehow solidify the jetted or the kind of deposited material. We can do it by simply solidification of a melted material, or if you have a carrier fluid, simply what you do, you may simply evaporate this carrier liquid inside your material, or lastly, you may do a quick photopolymerization process. If you have lights or kind of, let's say, photo beside your head, then with the help of them, you may start the initiation, the polymerization, and try to cure your photopolymer. And this was actually done in the objects. If you remember the video I showed you at the beginning of this chapter, I think it was called objects 1000 or 500. I forgot it, but they were simply using this idea. They have a quite complicated head. They have thousands of nozzles. They are jetting photopolymer, and on the side of this head, they have some UV light. Once this light is reflected on the jetted material, jetted polymer, it actually polymerizes, the UV light polymerizes the material in very low seconds, and maybe some milliseconds. And once they are jetted on the table or on the other layers, they will be solidified. So this is important, the last one here. So we need to have a phase change for sure, since for the drop generation, we need to have a liquid state. But this solidification or polymerization may happen during the droplet flight while drops are moving in air, or just after they impact with the the substrate or the previous layer. These are critical issues for jetting processes. And obviously, the jetted layer should be perfectly bonded to the previous layer to prevent any delamination process. We don't want these laminates actually separated from each other. Another issue is that your speed shouldn't be too much, otherwise you may be damaging the previous layer, and that will result in low dimensional accuracies. Another thing in these jetting processes is that some companies have different monitoring systems. Even they are using some powerful cameras or different kind of sensors, so that the performance of the nozzle will always be the same. And they may have some cleaning cycles. I think we have, probably I showed you in one of the videos, the head was moving. I think it was in X1. They were printing a sand mold for metal casting. They were cleaning the head after, let's say, few layers. They have a special region inside the bed. They move their head to that region and do some cleaning operation. This is quite important for the performance of these nozzles. Since we have thousands of them, if any of these nozzles are clogged, if it's closed, then we cannot have the part actually fabricated. So this is why we need to have periodical cleaning cycles. Any questions after this point, after the challenges of jetting processes?
Hocam iki önceki slaytla alakalı bir sorun vardı. Dropletler giderken eğer solidificate ederse nasıl yapışacak bir önceki layer'a?
They're not fully solidified. If it's done during the flight, probably they are in the phase transformation stage. not completely solidified. Yes, you're right. If it's completely solidified, you cannot join them together. So here's there's a critical, let's say, edge. At that edge, you need to have kind of semi-solid state so that they will be joined together easily.
Tamam, teşekkür ederim.
Not completely liquid, not completely solid, so you should be in between. Other questions, guys? And now we will focus on some droplet formation methods, how we are going to generate these drops. Initially, we can classify them into two categories. The first one is continuous column liquids. The one actually on the right-hand side, this is here. As you see, we have a continuous column of liquids. And at the tip of this liquid, you can have a drop. And once the weight of this drop is higher, we will have the droplet generated. Or you may have simply discrete droplets generated inside our system. But in that case, you need to be careful about controlling these drops. Now let's focus on the continuous mode first. In the continuous mode case, we need to have a steady pressure on the reservoir. On the upside, assume that this is a continuous liquid form. So we need to have a constant pressure on top of this region. So with the help of it, we can always generate such continuous column of liquids. But for the discrete one, obviously, we don't need to have a constant pressure. In the discrete one, we will sometimes increase the pressure. With the help of it, drop will be generated and then decrease it once again. So if you have kind of breakups, then we need to actually have breakups. Otherwise, it will always be a continuous, like in the case of fused filament fabrication. We don't want to have it since our aim is to generate droplets. That's why we need to have kind of vibrations, perturbing, and for that purpose, we have some extra equipment around the head. We may use simply a charging field, and these, in addition to the charging field, we need to also have some extra equipment to direct our drops to the proper, let's say, positions on the table. Here's the thing, actually, in this continuous mode, you'll see we have the continuous supply of liquids with the help of a pump. And then we have our actuator. It can be any actuator, a thermal actuator, a mechanical actuator. And then we have, as you see, a continuous liquid supply column is generated here. But inside this charge driver, we need to have drops generated. And then later, we need to have such a deflection plate so that they will be directed on the plane, onto the substrate here. And beside your, actually underneath your nozzle, you may have such extra equipment so that we will not have many drops on the table. So if you, for instance, if you don't have a droplet catcher, what will happen? Instead of this position, since we want these drops actually jetted here. But if you do not have a catcher, then probably you'll have some extra drops around, or even maybe here. And we need to have maybe a mirror version of it here so that you'll only have drops at this point, not beside, not other regions. Otherwise, if you look at this top view, if this is an kind of a line we are trying to fabricate, we may have some extra splashes around, and that will obviously decrease the resolution, and you need to do maybe more post-processing. So these couples are an important component. Any questions, guys, about continuous mode of jetting?
Hocam ben bu deflection plates'in ne işe yaradığını anlayamadım hala da.
Deflection plates, since they are kind of electrolyzed, you will have, if you don't have deflection plates, then you may have more drops flowing in these regions. But if you have deflection plates, as you see, we have high voltage and ground here, so they will be kind of directed. They will be flowing through the center of this region. So with the help of it, we have kind of a channel, an imaginary channel. Otherwise, we will have more extra drops catched by these catchers, caught by these catchers. Any other questions? Okay, now let's focus on the second one. This is also sometimes called as, I'm sorry, sometimes called as drop-on demand mode or DOD mode. It's the discrete version of the continuous mode. So these are simply directed from the nozzle, generated from the nozzle, so it's much simpler, and we can have different types of actuators. You may have thermal, electrostatic, piezoelectric, acoustic, or other types of actuators can be used to generate such drops directly from the nozzles. We don't need to have an electric field or a charger kind of things. This is much simpler, so that's why most of the commercial systems are using DOD. This is named as drop-on demand. As you see, their speeds are quite high. The radius of the drops are usually around 25 to 120 micrometers, and their frequencies are very high. In a second, they can generate to thousands of these droplets. Here is the schematic of drop-on-demand type of droplet generation. Let's have a look at here. As you see, in this configuration, they are using an thermal actuator. So we have a kind of a material here. Once you increase the temperature of it, probably it will be expanded, its size will be increased, and you will be having some pressure develop inside. And with the help of this pressure, we will have a drop generated. And this is done in less than a microsecond. And we can also do it with a piezoceramic type of material here, you see. Again, but this time is actuated with an electric source, as you know. Once it's actuated, again, we will have pressure develop here and a drop generated. And this is actually not a mechanical thing, it's just showing the pulse train. So at these regions, assume that this is time. On this axis, we have time, and on the, let's say, vertical axis, we have a kind of pressure. It might be pressure, or it might be heat source, the amount of heat source, or it might be the volt of your electrical actuator. So depending on you are turning on the actuator or turning off it, you will have such drops generated from your head. And again, obviously, we need to have a continuous supply of liquids. Otherwise, the same pressure value will not be enough to generate the drops. And this one is obviously the table. Table is moving, so the drops will be actually deposited after each other, and they will be joined together. Any questions on this drop-on demand mode?
Hocam bir şey sorabilir miyim? Bu daha mı isabetli şey bakımından? Hani bed üzerine isabetli düşüş bakımından dropletleri.
Yeah, this one is better and much simpler. That's why actually commercial products are using this one. And I think the generation speed of this one is also better. With the other one, you cannot go up to 2000, but DOD mode is quite useful for high speeds.
Hocam diğerinin kullanım amacı ne oluyor o zaman? Ne avantajı var buna göre?
not much advantages. In the earlier days, they start using different ideas since they want to have the best one. But now they conclude that this is the best one and they are using drop-on-demand mode. Since this is research, you may start with wrong ideas and try to see or try to improve the performance of it. But at the end, they show that this one is much better. There is a question how these 2000 drops are generated. Especially it's generated with piezoceramic kind of actuators. They are much faster. With heater, you cannot generate that amount of drops, since, as you know, heating systems are quite slow systems. You cannot easily increase the temperature of this heater and then decrease it, since you need to wait for this heat to be dissipated. But piezoceramic kind of actuators are highly fast. They can respond in some nanoseconds even. So if you apply some voltage to piezoceramic type of actuator, you can expand this part and a drop will be generated. Any other questions? Okay. So as I said, DOD is preferable. It has smaller droplet size. Its accuracy is much better. And since you can have high frequencies with piezoelectric type of actuators, it's more widely used in this type of systems. Any questions? Okay. And let's have a look at some energy levels, some basic modeling of this process. It's actually on the energy side. We will just focus on the amount of energy required for droplet generation. You see, this is the impart energy. This is the energy we need to give to our head. What is that? It consists of a kind of a loss, and this is for conversion of kinetic energy to thermal energy. And another thing, we are generating a new surface. So we are generating a new drop. This drop has a surface. So we need to spend some energy to form these free surfaces. Another thing, since we are jetting it, it should have some speed. It will need to collide with the previous layer or the substrate. So that's why we need to apply some energy for the kinetic energy of these drops. So if you apply all these energies, then you can simply generate the drops.